The next thing that I want to talk about in this series of videos is called the isomorphism theorem for rings, and this is a really important theorem that comes out of this chapter, and what it does is it reconciles something that we've seen so far. So I think in this second video on ring homomorphisms, we established that if we start with an ideal I of R, then we automatically get a ring homomorphism phi, mapping the ring R to the ring R mod I, via the element little r inside of R maps to R, the coset R plus I. So in other words, I mean that's a lot of technicalities, but if we start with an ideal of a ring, then we can get ourselves a ring homomorphism from that ideal. What we established in the previous video is that almost a converse to this statement. If we start with phi and it's a ring homomorphism from R to S, then I can obtain an ideal of the original ring R by looking at the kernel of this ring homomorphism. So on the one hand, the first bullet point is saying, if I start with an ideal, then I get a ring homomorphism. The second bullet point is saying, if I start with a ring homomorphism, then I can get myself an ideal. And so it seems that we have some type of correspondence between ideals of a ring and homomorphisms of a ring. The theorem that we have, which is called the first isomorphism theorem for rings, is saying that the correspondence is really special. And so in particular what it says is if phi is a ring homomorphism from R onto S, then R mod the kernel of phi, that factor ring, is isomorphic to S as a ring. Right? That these are really and truly the same ring. If I start with a ring homomorphism from R and I want to stress the word onto, if I start with an onto ring homomorphism from R to S, then S is really the same ring up to a ring isomorphism as the ring R mod the kernel of phi. Now that's the statement of the theorem. What I want to do now is cover a couple of examples that discuss how we use this theorem. So let's go back to an example that we studied a little while ago. Let's let R, the ring R, be the polynomial ring, real numbers adjoint X, and let's let S be the ring of complex numbers. And we're going to take a map phi that goes from R to S that sends the element X to the number I, and then it takes any other element that happens to be a real number. If R is a real number, it just maps it to itself. And then what we're going to do is we're going to extend phi, according to this definition, to be a map on all of R adjoined X accordingly. So what that means is extend the map so that we force it to be both a group homomorphism and a ring homomorphism. I've given an example here just to hopefully highlight what I mean. So I've defined where X needs to get mapped to under phi. I've defined where real numbers have to get mapped to under phi. How would I figure out what is phi of the polynomial 3x squared plus 9x plus pi? And the answer is I extend phi to automatically make it a ring homomorphism. So I take all of the additions that I see happening inside the parentheses and I make it so that phi distributes over those additions. So the first equality I should have is something like phi of the quantity 3x squared plus 9x plus pi is equal to phi of 3x squared plus phi of 9x plus phi of pi. And then I'm going to also allow my phi to respect things like multiplication and exponentiation. So that first term, that phi of 3x squared, should be phi of 3 times phi of x squared. Phi of 9x should be equal to phi of 9 times phi of x, and phi of pi should be just what it's defined to be. The phi of the 3x squared becomes the phi of 3 is just going to be a 3. Phi of x squared is going to be I squared, which is negative 1. So that phi of 3 times phi of x squared term, I've rearranged it in this equal sign. That's equal to the minus 3 that we see occurring at the end. Let's see if you'll see this over here. Now the phi of 9 times phi of x, which is the phi of 9x term, that corresponds with the 9i that I have right here. And the phi of pi is just equal to pi by the way it's defined. So hopefully that makes sense. We're defining what phi should be on things like I and R, and then we're making sense of phi by just sort of forcing it to follow the rules of ring homomorphisms for a general element of R. And now let's see what's going on here. If a plus bi is a complex number, let's look at phi of bx plus a. Again, I've switched the order of the addition because my rings are commutative here, but phi of bx plus a is equal to a plus bi, and so this establishes that the map that I've defined really is an onto map, which was a requirement of the theorem on the previous page, this first isomorphism theorem. By the first isomorphism theorem, so I've got a ring homomorphism, it's an onto homomorphism. By the isomorphism theorem for rings, R modulo the kernel of phi is isomorphic to the complex numbers. Now it can be shown, this is a little tricky and we won't show it here, but it can be shown that the kernel of phi is the ideal generated by the polynomial x squared plus 1. And therefore, this is the factor group, R mod, the ideal generated by x squared plus 1, that's isomorphic to the complex numbers as a ring. Now this example, this R modulo the ideal generated by x squared plus 1, this is an example that we worked out when we were talking about factor rings. So we did establish in that case that the ideal generated by x squared plus 1 was maximal, and we know that R modulo a maximal ideal is giving us a field. The question was just, well, what field? There are lots of fields, and this example is showing us that in fact the field we get when we consider R modulo the ideal x squared plus 1 is the complex numbers up to isomorphism. Here's yet another application of that first isomorphism theorem for rings. And it's telling us something really cool actually about fields. So let's suppose that f and f primed are two different fields. And let's suppose that phi, mapping from f to f primed, is a ring homomorphism, where we also assume that the kernel of phi is not all of f. The conclusion of the lemma is that f is isomorphic as a ring to the image of phi. And now let's prove it just to see how we do something a little bit more abstractly. But here's the idea. We know by our theorem from the last video that the kernel of phi is an ideal of the field f. And what we're given is that the kernel of phi is not all of f. Something that we've proven by now, this was easily listed as an exercise or in your homework somewhere, is that fields only have two ideals. They have two ideals. They have the whole field and they have just the set containing 0, and those are the only two ideals of a field. And what I've just done is, with my assumption that the kernel of phi is not f, I've said the kernel of phi, it's not equal to the ideal f. And what we have then is that there's no other choice but for the kernel of phi to be equal to the set containing 0. Now, one of the properties of ring homomorphisms that we had was that if the kernel of phi happens to be equal to just the set containing the additive identity, then the map that we have is a one-to-one mapping. It's injective. So the map that we have from phi, going from f to the image of phi, is an injective map. And by definition, the image of phi is the set such that phi maps onto this. Right? So we automatically map onto the image of phi just by the definition of phi. So if I look at phi not just from mapping from f to f prime, but if I look at phi as a map from f to the image of phi, where it happens to be an onto map, I've just shown that by the assumptions of the lemma, this is also a one-to-one map. And what we have then is that phi is a bijective ring homomorphism from f to the image of phi. And that's what it means for two fields to be isomorphic. What's really cool about this lemma is it's using this isomorphism theorem for rings, but it's also telling us that fields are basically unique up to isomorphism. Really, if you have two different fields, they're either totally different or they're exactly equal to one another. So the only thing that's similar to a given field is just the set containing 0, which is in a way similar to everything, and then just itself. It's kind of its own entity. It doesn't really share any properties with any other fields that you might like it to. So something that you could do as an exercise, thinking of this now, although I didn't add it to the slides, but something that you could do as an exercise is you could show that the field R2 is isomorphic to the field of complex numbers using this first isomorphism theorem, and I think that that would be a really good exercise to work out.